So differentiation, integration, high school stuff, but we all forget it and we need a maths book to be able to do it. Laplace realised this, a man called Laplace, unsurprisingly quite French I think, and I think he got frustrated by the same things that we do, that calculus is a bit messy, yeah? But algebra, remember good old algebra? You take something from one side, if it's in the multiply position, put it in the divide position that side. If it's in the add position there, you subtract it when you move it across the equal side. We all know all that rubbish, right? So what Laplace said is, well, I actually want something that describes that to me in a circuit, but I don't have to use differentiation and integration. And he came up with this really quite simple way of doing it. It's got more complicated claims as for other signals, but if everywhere we see a capacitor, we replace it with 1 upon SC, and everywhere we see an inductor, we replace it with SL. Now we can just use basic algebra and we can solve for anything that's got inductors or capacitors in it. There is nothing else really. There is nothing else really. So, well, where does that get us? I mean, that's not... We've just got this wonderful wisdom that we can now replace this. Well, what does that mean? Well, it actually means that S is just 2 by F, right? Because that's what it says up there. So, Laplace got all this fame and fortune. Well, I think he died a pauper, but he got all this fame for coming up with replacing S with 2 by F. Not really, because what he's saying is that S is complex, but let's not go into that. What he is saying, though, is if I now take this circuit that we're all familiar with, so here I am, classic low-pass filter, and I do this now. Remember the rule? I just replace all capacitors with 1 upon SC, all inductors with SL. So what I end up with is here, R, and I end up with 1 upon SC here. How does that help us? Here! Look! Look! If we now regard R2 as a complex impedance, I can just put that directly into that equation. So I can say that V out is equal to V in R2, which is this 1 upon SC, all over. Don't worry about top heavy fractions. Always go with the top heavy fraction and then simplify afterwards. R1, which is still just R, plus 1 upon SC. So that's my answer. What a mess. What a terrible mess. Well, not really, because what I've got here is I've got SC here, that SC comes down here, and what I end up with is V out is equal to V in 1 upon SCR plus 1. That's what that tells me. So now I've got an expression, just like I had before, but now I've got an expression which is only talking in terms of C's, R's, and frequency. That expression worked. That's great. That's great. We can do it the other way around. So we can have a C here and an R here, and plugging the numbers back in here. So V out equals V in. Only this time it's not 1 upon SC, it's just R. And R1 is 1 upon SC, and the other one is just the plus R. Yeah? There's various ways that you can deal with that, but actually that's not an inconvenient way or form for it to be in anyway. You could multiply top and bottom by SC if you wanted to, and what you get is you get V in SCR upon SCR plus 1, if you think that's neater. It's just the same way of doing the same thing with you. Didn't really tell you a great deal more than you already knew, because obviously as S, which is 2 pi f, gets higher and higher and higher, we get 1 upon a very, very big number. So what's 1 upon a very big number? Very small number, right? So what that tells you, as frequency gets high, the output goes very small. Well, that's what we expect, because it's a low-pass filter. So we've got this expression now telling us the magic of what that circuit does, assuming we didn't know anything about the behaviour of a capacitor. There's something somehow magic about that, I think. Because you're using algebra, not calculus. But you're coming to the same conclusions. Now, anyone want to photograph that before I take it up? No? No? Yeah, no? Sorry. So, that's that magic. Do you need to know this for the assignment? No, you don't. No, you don't. But what this is doing is it's filling in some gaps for you. So, you know, all those funny things that are on the board, what do? What are they there for? Why do you want a capacitor? Why do you want an inductor? Well, because they behave like this. Now, we can go up the tree of complexity. We can go up the tree of complexity quite quickly, because what we could do is we could do this. And I do prove this inside the notes. I'm not going to do the full proof here because I don't think most of you will understand it first time round. But there is a proof of this inside the notes for, these are called LC circuits. So you'll notice you've got a capacitor and an inductor there together. Welcome to the world of radio. Because if I just do this, and this is what our amateur radio club signal is, or sign rather, is. And that's an antenna, supposed to be. That's a radio. It's not very good radio, because it doesn't rectify anything, and all of the signals are there, and it's not very selective, and all the rest of it. So if I'm a bit cleverer, I can make the beginnings of a crystal set, so I make this a variable capacitor. Now I can tune into different stations. That's it. So if I can tune into different stations, what do you think that circuit does? So I can select one station from all of the stations that are out there. Bandpass, yes. So when you have that kind of configuration, you've got kind of a bandpass filter. Why is the resistor in there? Otherwise you can't simulate it. Because otherwise the input's the same as the output. That's a problem to you. So that's why you always have, you'll see these things quoted as R, L, C circuits. RLC circuits. Now if we're going to resolve this, so let's just take the maths a little bit further. And maths is nothing to be scared of as long as you stay within the realms of what you already know and then add a little bit on each time. You've got two components there in parallel. So if I did this and I said, what's the combined resistance of that? Probably half, 3/4 of you in the room would be able to do that, and the other quarter would probably find out from a Google search, right? To work out those, if this is R1 and this is R2, the combined resistance is R1, R2 upon R1 plus R2. Okay? So if I do this for a tuned circuit, that's what these are called, tuned circuits, because what happens? The inductor becomes charged on one cycle, creates a magnetic field around itself, the inductor saturates, discharges, produces a voltage across the capacitor. The capacitor charges up to the maximum voltage it can, whereupon it collapses and releases current, and the current goes back into the inductor. So what you have is what's called a tank circuit. So exactly the same as if you get a tank of water, or you've ever watched anyone with a big cup trying to go upstairs, you can't keep the water in. Why can't you keep the water in? Because it sloshes from side to side and you can't stop it. The more you try to stop it, the worse you make it. So it's called a tank circuit, because you imagine a tank of water and try moving with it, and it does that, doesn't it? Pushes one way, pushes the other way. That's what this does all the time, only we can design the frequency that it does the sloshing. Okay? So if we've got R1, R2 on here, I'll just stop the video, because otherwise it's going to go over YouTube.